By the way, these kinds of problems are sometimes called open middle problems. They're called open middle because the beginning of the problem is set, it's known, it's a structure. The end of the problem is known, namely that this equation is true, but then you need to specify what goes on in the middle, namely what digits are actually filling these blanks. So who came up with one possible solution to the digits 1 through 9 not being used more than once, filling in these boxes to make this equation a true statement? Just tell me for right now what the number was on the right-hand side of your solution. So start with your team.
So we did 14.
Yeah, what was the number on the right-hand side?
Like 7.6.
7.5. Okay, so there's one possibility. What did your group? 7.6. I'm sorry. 7.6. What did your group have on the right-hand side? 3.5. And what did you have for your right-hand side? 2.5. So that's interesting. We already have 3 possible solutions to this problem. So let's take a look at the other. Let's take a look at the other digits that ended up filling these slots. Let's start with your 7.6 solution. How did you fill out the fractions on the left-hand side to make this sum 7.6?
We first did 14 over 2.
14 over 2. Okay.
Which would give us a whole number.
Okay.
7. And then we did 3 over 5.
3 over 5.
Which is 0.6. So
Yeah.
7 plus 0.6 plus 7.6.
Look at that. Great. That seems like it works. Let's double check. Are they using any digits more than once? 1, 2, 3, 4, 5, 6, 7. That's cool. They're even using all consecutive digits. That seems like it works. Before we look at the other 2 solutions that were proposed here, let's take a step back and try and redo this with avoiding using decimals. Let's suppose that what we wanted to do was to add these 2 fractions, 14 halves plus 3/5, but do it as fractions. So let's bring our fraction addition strategy into the mix. How would I add these 2 fractions? What's the first thing I would need to think about? Common denominator. So what's a good common denominator, or rather, what's any common denominator that I can use to add 14 halves and 3/5? 10. Remember, when adding fractions, we can always find a common denominator simply by multiplying the 2 denominators that were there. It may not always give us the easiest denominator to use, the smallest in other words, but it will always give us one that works. So we'll use 10 for that denominator. And once that's my denominator, how do I find my numerators? Yeah, multiply acrosswise. Numerator of one by denominator of the other. 14 times 5. 14 times 5 is going to give me 70. And then 2 times 3 is going to give me 6. Okay. Now my fractions are on the same denominator. How do I add them together? Denominator stays the same. And the numerator gets added. Great. 70 plus 6. That gives me 76. And so my fraction is 76 over 10. And remember, when you divide a number by 10, what happens to its decimal expansion when you divide a number by 10? Yep. That's the nice thing about dividing and multiplying by powers of 10 in the decimal system, is all it does is it moves the decimal point. It doesn't change the digits. So that's how we know that this fraction actually does line up with the decimal 7.6. And orange team, I just declared that you were orange team, has a solution to this open middle problem. Cool. What were the other digits that give you 3.5 in the sum on this side? That was yours, right? 20 and 4 over 8. All right, let's double check. We haven't used a digit more than once. 1, 2, 3, 4, 5, 7, 8. Seems like good shape. Let's do this again as a fraction addition problem. Just again, flex those fraction addition muscles. 21 over 7 plus 4 over 8. So what's going to be a denominator that we can use that's common for both of these fractions? For some reason, this was the number on the times table that I always had the most trouble remembering when I was learning times tables, 56. The way I ended up remembering it is a little device, 5, 6, 7, 8. That worked for me. I don't know why. But yeah, 7 times 8, 56. That gives me a common denominator. Then all we would have to do is find the cross products to get the numerators. 21 times 8, 168, and 7 times 4, 28. Multiplying those cross products. Then add across the numerators. And so here's an example where it's not really clear to me, in the beginning at least, what's 168 plus 28? That'd be 196. 196 over 56. So it's not clear to me looking at this fraction why it should be the same thing as 3.5. So how could we make this fraction simpler? What are some things that we could do to bring this fraction into simpler terms? So how do you reduce a fraction into lower terms? What do we end up looking for here? Reduce a fraction into lower terms, we just need to find a factor that goes both into the number 196 evenly and also into the number 56 evenly. And don't have to bite off more than we can chew here. What's a number that we definitely know goes evenly into both of those two things? 2. So let's do that just to sort of get the ball rolling. Once I know that 2 goes into both of those things, I can divide by it, which is not the most fun division problem in the world, but, you know, definitely had worse. 98 and 28. And what do 98 and 28 have in common? Possibly a lot, but definitely a 2 again. So that's another thing you can do, is don't feel like you have to reduce a fraction all in one bite at the same time, right? Take little bites, because anything you can do to make those numerators and denominators a little bit smaller will help you along the line. Eventually, maybe you'll find an even bigger factor that you can use to take an even bigger step towards lowest terms. And in this example, now what's a factor I can see with 49 and 14 that they have in common that's a little bit bigger? 7. So I can take and divide both of these by 7 in the numerator and denominator to give me 7 over 2. And 7 divided by 2 is 3.5. Or yet another way of understanding why that is would be to try to bring this fraction, 7 over 2, up to a denominator of 10. If I want to do that, how do I fill in this blank right here?
Times 10 by 5.
Yeah, how'd you know it was 5?
Because 2 times 5 is 10.
That's right. If I want to fill in that numerator, I observe that what I did to the denominator was I multiplied it by 5, and so I must do the same thing in the numerator. 7 times 5, 35. And when I divide 35 by 10, I'm really just moving the decimal point over and getting 3.5. So yeah, this is a solution that works as well. For the 2.5 team, what was the rest of your problem on the left?
14 over 7. And 3 over 6.
And 3 over 6. All right, let's double check. 1, 2, 3, 4, 5, 6, 7. So again, consecutive digits from 1 through 7, no repeats. Great. And 14 over 7, 2, 3 over 6, 0.5, 2.5. That works. And I won't rehash the fraction arithmetic with this example. So this is great. It's a problem that gave us a little task to do that involves some fraction arithmetic, a little bit of decimals, and that there are at least 3 different ways to do this. I don't know, personally, how many different ways there are to do this, but that would be a really interesting question for a math major to look at and try and say, all right, we found 3 different ones. How many different ones could we find? Those are the kinds of questions mathematicians like to ask and answer.